Now, circular motion we can understand similar to linear motion. So, let us start with an observer who is sitting here, and now for example you see the moon changes its place. Suppose it moves in an arc like this, and then you have the angular displacement. Now this you call angular displacement. It is a vector, but actually angle is not a vector. Angle is a scalar quantity. But angular displacement is a vector, and this could be counterclockwise or clockwise, therefore it is a vector. Now let's have a look. It does a linear motion along this arc, then we define theta as L arc divided by the radius. The radius is r. Now it is very easy to derive it. If somebody does an angular displacement of 2 pi, the arc length corresponding to this will be 2 pi r. Now if somebody does angular displacement theta, and corresponding to it there will be angular length L. Therefore, if we take the ratio, we get this relation. Now this is definition in radians. Okay, so this is just for the quick revision, and then we can define angular velocity omega as d theta by dt. Right? If angular velocity remains constant, we say uniform circular motion. Okay, now let me make a quick comparison. You have linear physical quantities, and you have, for the circular motion, we will say rotational. So this is actually beginning of rotational, and I usually do circular motion after Newton's law of motion. Okay, so rotational or in circular motion, what we do is, here we have the velocity u. So let's start with displacement. So we have the simple displacement s, and here we have the theta, here we have u, here we have omega, here we have acceleration a, here we have alpha. Now alpha is called the angular acceleration, and we are going to write them down. D theta by dt, d alpha is d omega by dt. Very well. Now these are few things. Another thing is kinematics is exactly similar. Here we have v is equal to u plus at. Here we have omega at any time is equal to omega initial plus alpha t. Right? And then we have for displacement s is ut plus half at square. Here we have theta is equal to omega it plus half alpha t square. Then we have v square is equal to u square plus 2as. Here we will have omega square is equal to omega I square plus 2 alpha theta. Now this description is valid until you have uniformly accelerated circular motion. Now after this definition, I am going to discuss briefly few more important things. Now until now in BITSAT there have been perhaps one question on this. There has not been a question on angular velocity. Okay, so let me discuss few more interesting things. So how do you actually relate the angular velocity with the linear velocity when a body is doing circular motion or even not doing circular motion? suppose okay, or let's discuss simply how can we understand circular motion. So suppose we have an object which we represent by P, R, right? At any point it makes an angle theta. We define its coordinate as r cos theta, r sin theta. Right, now this derivation is really important, from which we will know all the things about circular motion. So let's keep it a general. Position vector of P with respect to O will be given by r cos theta I cap plus r sin theta j cap. Right, if I ask you what is the velocity at any given instant, you will do dr by dt, and then you can easily see this will become minus r sin theta d theta by dt I cap, right, and then r cos theta and d theta by dt j cap. Now, if you look at the velocity, velocity in circular motion is given by, let's write r omega, because omega is d theta by dt, and you have minus sin theta I cap plus cos theta j cap. Now there will be a couple of questions based on this dynamics, and this is really important, and these sort of questions have appeared a couple of times. So let's be focused here. Now let's compare it with the r cos theta I cap plus sin theta j cap. Now what you can see here is V and R are perpendicular. So you can do R dot V, and you will see R square omega. I cap dot I cap will survive. So minus sin theta cos theta plus sin theta cos theta. Right. So you can see if the dot product is 0, that means in circular motion position vector and velocity are always perpendicular. And as you see here, the velocity is tangential, okay, and it is perpendicular to the position vector. So we can write r vector as magnitude times the radial unit vector. So you see this is the radial unit vector, and the velocity you can clearly write as r omega times the tangential vector. Right. Now let's do one more thing, and we know everything about circular motion in one shot. Very quick, very fast, okay. So please be focused. We are going to do nice things, okay. Now take the derivative of velocity, okay. Let's clear this board and we'll do it here. So just by simplest derivation without any memory, you can in 30 seconds revise the key concepts, and you will notice all of the questions that were asked in circular motion were based on theory that I am doing. Okay, so let's be very focused. Now the BITSAT attempt 2 is really important, and this is the only college of the level of IIT. So those who have had issues with JEE Advanced, who had problems with JEE Main 1 and 2, this is the moment for you to shine. And I'm going to show very easy questions are asked. Okay, let's take another derivative, and we know what is the acceleration. So dv by dt. So we are going to take derivative of this. Our radius is constant because this is doing a circular motion with a fixed radius. So let's keep it apart. And then everything is derivable. Okay. So we'll have d omega by dt. Now this is our alpha. Inside term we will keep that plus cos theta j cap. Then we'll keep the r, we'll keep the omega, we'll take the derivative inside. This will give me cos theta d theta by dt I cap plus minus sin theta d theta by dt j cap. So it's all about just accounting. You know, sometimes accounting is for money. In education, it's about I cap and j cap terms. Okay, so let's keep the r out, and here we have. Okay, so let us consider first the simplest motion. Let's consider omega is fixed. Omega is equal to constant. We don't have to, but let's live with it. Let's keep omega constant. And then this term will go away. The only term remains is this one. Okay? Now, this is the this is the special case we have taken for uniform circular motion. Okay, we want to know everything about uniform circular motion. Now that has been mostly asked for BITSAT. There has been no question on non-uniform circular motion, so we are not going to do in this class. Let's focus here, omega. So this is omega square. And you can see I can take a minus term out, so my acceleration becomes, you see, it's going to be really nice. Omega times this omega goes out. I can take this also omega out. Now I'm left with cos theta I cap plus sin theta j cap. Right? Now that was my interest. You remember I used a special term, this for radial direction, cos theta I cap, sin theta j cap. That means it's radial, and this was radially outward. Now here you see with the minus sign, so our acceleration is omega square r and directed radially towards the center. Okay, now this is really important point. You can imagine you have a friend sitting at the center and he is the observer. For him, everything would look like that, right? And that means this is the centripetal acceleration. Centripetal. Now this is really important point. Centripetal acceleration is for the observer who is sitting on inertial frame. So if he is sitting on the ground, he is not rotating in circle. He is at rest, so for him it would be centripetal acceleration, and its direction will be towards center. So acceleration is always towards center. You can think this, okay, by following line of thought. The body wants to go tangential, but you can imagine due to centripetal acceleration it falls down and it falls radially towards the center. Then it wants to fly away, it falls towards the earth. Now this is the way Sir Isaac Newton thought about moon, and then he gave the bold theory that moon is just a freely falling object. Now the moon was falling under centripetal acceleration. Okay, now some of you will ask me, right, some of you will ask me, what is centrifugal acceleration? Okay, so I'm going to tell you, if you have a coin, on this side is the centripetal acceleration, on the other side, okay, so the two sides of the coin have different names. Centrifugal. So you can see they are actually the same, okay, just in a second. Have you ever sat on a joyride? Okay, if you have sat in a joyride in a festival, what do you feel? You feel a force outward, right? So imagine if the observer is sitting here, okay, imagine the observer is you, okay, before it was your friend, and your friend thought all the time you are falling towards the center with the acceleration a, and that acceleration is omega square r, and it's a centripetal acceleration. But if it was you, you would feel, suppose you are here, you will feel a pseudo force, and this pseudo force is nothing but mass times the centripetal acceleration, right? So we define centrifugal acceleration also as omega square r, and it's just the direction of this acceleration is outward. Now you would ask, why are they same? Now they are same because you can imagine the body is doing uniformly accelerated motion. It wants to fly away tangentially, but it falls down, flies away, falls down, right? So to the observer here, it seems it's falling towards the center, right, with the centripetal acceleration. But actually, for the observer who is on this joyride, he is always feeling an external force, and this force is a pseudo force, and this is due to mass times the acceleration of the frame. So since he is sitting in an accelerated frame, he feels the force backward. Now this is what happens when you ride a car, bicycle or anything. When you accelerate forward, you feel a jerk behind, right? Because you're accelerating forward, you feel the pseudo force, right? So similarly, since this is doing circular motion, and imagine he is actually accelerating towards the center, so the observer will feel the pseudo force. So that's why we have to consider centrifugal acceleration and the centrifugal force. I think we have discussed quite important points. So let me go to the previous year questions, and then wherever necessary we will begin or we will do the theory, okay? So we'll do the banking on a road, we'll do, so in circular motion there will be many cases. For example, when you turn on a road, if you are on a bicycle, right, what happens is when you take a steep turn, you tilt, right? You tilt towards the center of the circle where you are doing, right? And for road safety, they keep lot of friction on the road when you are doing a turn. But also they make the road banked. So the side of the road goes up, and then when the person crosses, they get some help, okay? So based on all these concepts, there are going to be questions. Okay, so let me clear this board, and then we are going to introduce the questions. Okay, so just be patient. I have all the questions. I think about 15 to 16 questions have appeared. That means every year almost one question has been asked from circular motion. Okay, so we will do circular motion with friction. We'll do circular motion with the banking of the road and all. Okay. So let me clear the board quick. Okay, we'll start with something easy and then we'll go in depth. Okay, तो देखिए ये बहुत ही इंटरेस्टिंग और इजी टॉपिक है. इसमें 100% स्कोर किया जाता है, इसीलिए आज मैं आपके लिए ये लेके आया हूँ. इसके बाद हम रोटेशनल मोशन करेंगे और उसमें हमें काफ़ी इंटरेस्टिंग क्यूज मिलेंगे. ओके, लेट्स मूव ऑन. Okay, so let's see this question. This is the first question. I really wanted it to be easy for you. Okay, when a particle is in uniform circular motion, now please answer this. See, I did the very quick derivation and I don't remember any things. Okay. Okay, so how would you look at this? It does not have first option, radial velocity, radial acceleration, not possible. Radial velocity, tangential acceleration, not possible. Oh, it is. Oh, so when a particle is in uniform circular motion, it does not have. What it does not have? So the velocity in uniform circular motion, velocity is omega r tangential, right? And acceleration is omega square r, and it is minus radial, right? So the acceleration is okay. So based on these, so does not have tangential velocity and transverse acceleration. So actually it has tangential velocity. So let's see. Okay, you know, this question is not written properly. We should have, when a particle is in uniform circular motion, it does have tangential velocity and acceleration is radial. Let's move on. इधर लाके क्लिक होता है, करें? Okay, let's look at the next question. Okay, a body is traveling in a circle at constant speed. Constant speed means it's a uniform circular motion. But it is accelerated because we know acceleration is radial towards, has a constant velocity, has an inward radial acceleration, this is true, has an outward radial acceleration. Now, the speed is constant, but the velocity is not constant, right? So, the first option is incorrect. Second option is not accelerated. We just saw there was centripetal acceleration. So, the option B is wrong. Third option is has an inward radial acceleration. That's the correct. So, our answer is C. Okay. Back. Piche. Okay. So, is inward and radial. Let's move on. So, now we have a question. It says velocity and acceleration of the particle are given like that. At any instance, the radius of the circle is. See, what did we learn? We learned acceleration A is given by minus omega square r and radial unit vector, right? If I write in terms of velocity, I forgot to mention the velocity, linear velocity is given by omega cross r. Okay, so if somebody is doing circular motion, then V is equal to omega r. It's better to remember in vector form. So, in scalar form, the magnitude V upon r is omega. Now, if you plug it in the magnitude of acceleration, what do you get? The magnitude of acceleration will be V by r square into r because it was omega square r, right? So, this will be V square by r. Now, they have given in vector form. So, why shall we worry? Okay, we can get the radius as V square by a, right? Either we write the magnitude of V squared divided by a, right? So, we can quickly do the magnitude of V is 2, so 2 square by a is square root 2 square plus 4 square, right? Because our acceleration is given in vector form. So, we can very well find out, right? So, we can easily take out 2 square root 1 plus 4, and then this will be 2 square, so this will be 2 by root 5. Okay, let's think about it. No, let's go back. Velocity and acceleration are given. So, acceleration is V square by r. So, r is V square by a. Now, the magnitude of a is just square root of 4 plus 16 is 20, so 2 root 5. So, I think it is 2 by root 5, and if you write it down, 2 root 5 by 5. Okay, so let's approximate. This is about 2 by 5 of 0.7. .4 by 5. Okay, so it's 0.3 meter actually. So I don't know, the options are not correct. Let's move on. So I think this would be the best. Okay, let's move on. So in order to move, अगले सवाल पे जाने के लिए हमें स्लाइड पे क्लिक करना होता है. Okay, so let's have a look at this question. अब देखिए ये सीधा सीधा सवाल जो मैंने थ्योरी डिस्कस की थी है उस पे बेस्ड है. तो सर्कुलर मोशन में ये पैरामेट्रिक फॉर्म है, इससे हम बहुत इजीली इसकी सारी डेरिवेशंस कर सकते हैं. सो लेट्स मूव ऑन. द वेलोसिटी ऑफ पार्टिकल. सो वी डिड दिस केस, पोजीशन वेक्टर दिया है. सो द आंसर विल बी the velocity of the particle is perpendicular to the position vector, right? So our answer is D. Okay, so in order to go अगले सवाल पे जाने के लिए हमें केवल क्लिक करने की ज़रूरत होती है. कभी कभी हम सो जाते हैं, एक ही काम है लेकिन फिर भी. ओके, सो लेट्स मूव ऑन. अ पार्टिकल इज मूविंग ऑन अ सर्कुलर पाथ. द एक्सेलरेशन एंड मोमेंटम वेक्टर्स एट इंस्टेंट. हमें एक्सेलरेशन और मोमेंटम वेक्टर दिया है. देखिए एक्सेलरेशन दिया है और p दिया है. p इज mv और a दे रखा है. अब हमें मालूम है सर्कुलर मोशन में क्या होता है, A is perpendicular to P. तो इसमें गिवन है एक सर्कुलर पाथ पे है, वो डेफिनेटली होगा अगर ये ट्रू है. ओके, तो ये तो ट्रू लग ही रहा है. अगर आप डॉट प्रोडक्ट करें A डॉट P. ओके, A डॉट P करेंगे. 6 2 12, I cap 1, 4 3 12, -12. तो ये आ गया 0. ओके, इज अ यूनिफॉर्म सर्कुलर मोशन. अब देखिए यूनिफॉर्म सर्कुलर मोशन के लिए हमें क्या चाहिए पड़ता है, ओमेगा इज कांस्टेंट. ओके, सो with only knowledge of these two things, it is really hard to predict if it is uniform, right? Circular motion with tangential acceleration. देखिए कभी भी tangential acceleration नहीं होता है, tangential retardation भी नहीं होता है. I mean there can be non-uniform acceleration. अब देखिए non-uniform तब हो सकता था जब ये time dependent होता. अब इन्होंने दिया है the acceleration and the momentum at an instant of time. किसी इंस्टेंट पे ये है. ओके, तो इससे हमें टाइम डिपेंडेंस नहीं पता चलती है और इससे हमें राइट टेंजेंशियल एक्सेलरेशन और रिटार्डेशन भी नहीं पता चलेगा. सो दिस क्वेश्चन इज रियली सिली. ओके, so we cannot say anything about motion with the knowledge of just A and P. Okay, so I think the D is the answer. Let's move on. Okay, so the answer is D. Okay, let's move. अगले सवाल पे मूव होते हैं. देखिए ये बड़ा ही अच्छा सवाल है. देखिए ये हमारी डेली लाइफ में होता है. जब भी हम साइकिल से जा रहे होते हैं और हमें कहीं स्टीप टर्न लेना है तो हम क्या करते हैं, अगर हाई स्पीड में हो तो जिस डायरेक्शन में टर्न ले रहे हैं, आई मीन जिस सर्कल में टर्न ले रहे हैं उसके सेंटर की तरफ टिल्ट हो जाते हैं. ओके, यू कैन इमेजिन यू आर राइडिंग अ बाइसिकल. ओके, आई एम जस्ट ड्राइंग विद दिस. नाउ यू आर टेकिंग अ कर्व्ड पाथ विद द सेंटर ऑफ द सर्कल हियर, राइट. तो आप क्या करेंगे, वर्टिकल से किसी थीटा एंगल पे टिल्ट हो जाएंगे। अब यहाँ पे क्या कहा गया है, ये सेम एग्जैक्टली केस है। अ पर्सन with his hands in pocket is on ice skating. Okay, so hands in pocket and he is doing ice skating. Okay, so he takes a sharp turn. You will see they usually tilt when they take turn. Describes a circle of radius this. So उन्होंने r दे रखा है, r is 50 meter. Okay, now what is going to happen if he is taking this? Then suppose this is the center of gravity, he will feel mv square by r, right? And then there will be normal reaction from the ground like this. Let's ignore friction. Okay, friction is not needed for this. आप देखिए, this is a remarkable thing. Although friction helps, but you don't need friction to take turn. That's why it is ice skating case. देखिए ice skating में जब भी आपको टर्न लेना होता है, आप देखेंगे जब वो टर्न लेते हैं तो the rider will tilt in certain direction depending upon which direction they have to move. तो देखिए weight इसका डाउनवर्ड है mg. अब देखिए जो नॉर्मल रिएक्शन क्या करेगा, इसका एक कंपोनेंट वेट को बैलेंस करेगा n cos. Suppose this is theta, this is also theta, n cos theta will balance the weight, and n sin theta will balance mv square by r. तो हम क्या लिख सकते हैं, n sin theta is mv square by r and n cos theta is mg. So if you take the ratio of these, tan theta becomes v square by rg. Okay, तो अभी इसकी वैल्यूज डालेंगे हम. v की वैल्यू क्या है, 10 मीटर पर सेकेंड स्क्वायर. देखिए 10 स्क्वायर, r is 50, सब कुछ SI यूनिट में दिया हुआ है. g is 10. So this will turn out to be in radians and this will be 1 by 5. Therefore, the angle of inclination theta with respect to vertical is going to be tan inverse 1 by 5. Okay, so our answer is B. Okay, so देखिए ये सर्कुलर मोशन का पहला सवाल होता है और बहुत ही इंटरेस्टिंग फिनोमेना है. ओके, अब देखिए ये नेक्स्ट क्वेश्चन डेली लाइफ का है. आप जल्दी से देखिए जब तक मैं बोर्ड साफ करता हूँ. ओके, वेरी वेल. तो इस क्लास के बाद हम बहुत जल्दी से कल ही रोटेशनल मोशन और ग्रेविटेशन कंप्लीट करेंगे. इसके बाद मेरा प्लान है कि प्रॉपर्टीज़ ऑफ मैटर, इसमें फ्लूइड बहुत ही इंटरेस्टिंग है. मैंने देखा करीब जितने सवाल रोटेशनल मोशन के हैं उतने ही सवाल फ्लूइड्स के हैं. अब फ्लूइड क्या है, बहुत ही आसान टॉपिक है. इसमें ज़्यादा से ज़्यादा क्वाड्रेटिक इक्वेशन यूज़ होंगी. ओके, तो मैं कल रोटेशनल मोशन, ग्रेविटेशन के बाद कुछ ऐसे टॉपिक्स पिक करूंगा जिनमें आपके बहुत ही हाई मार्क्स आ सकते हैं या जिसमें इजी स्कोर किया जाता है और उससे काफ़ी क्वेश्चन आते हैं. ओके, सो लेट्स फोकस ऑन दिस क्वेश्चन. द मिनिमम वेलोसिटी with which a car must traverse a flat curvature of radius 150 meter and the coefficient of friction 0.6 to avoid skidding. और देखिए यहाँ पे क्या है, एक फ्लैट रोड है ना, और वो भी कर्व्ड रोड है. तो देखिए कोई भी चीज़ अगर कर्व्ड रोड पे है, सपोज दिस इज द कार एंड इट इज टेकिंग द टर्न, what would happen? It will experience mv square by r, right? Now they have given r and we have to find v minimum. ओके इन्होंने कोफिशिएंट ऑफ फ्रिक्शन भी दे रखा है, तो अगर हम इसका साइड व्यू बनाएं तो देखिए कार का क्या हो रहा होगा, इसका वेट डाउनवर्ड्स mg, ये नॉर्मल रिएक्शन फ्रॉम द ग्राउंड। अब इस डायरेक्शन में mv स्क्वायर बाय r लग रहा है, तो फ्रिक्शन क्या कोशिश करेगा, फ्रिक्शन विल अप्लाई इन दिस डायरेक्शन, राइट? सो वी नो हाउ मच इज फ्रिक्शन, फ्रिक्शन क्या होता है म्यू n, और हमें n क्या दिया हुआ है mg, राइट? और फ्रिक्शन क्या करेगा, mv स्क्वायर को बैलेंस करेगा, mv स्क्वायर बाय r, और फ्रिक्शन भी मैक्सिमम होता है म्यू n, ओके? तो हमें कंडीशन क्या मिल गई, म्यू n, so mu mg should be greater or equal to mv square by r. तो देखिए इसमें v क्या आ जाएगी, म्यू जी आर, for safety purpose the velocity should not be more than this, ओके? एक्चुअली इस क्वेश्चन में मिनिमम की जगह मैक्सिमम वेलोसिटी होना चाहिए था, क्योंकि सेंट्रीफ्यूगल फोर्स की वजह से ये आउटवर्ड्स जाती है, इसकी वजह से स्किड होती है ना? तो इसमें मिनिमम की जगह मैक्सिमम वेलोसिटी होना चाहिए था। अब ये थोड़ा सा मिस्टेक है, म्यू की वैल्यू डालते हैं 0.6, g is 10 and r is 150, तो देखिए 0.6 का 6 हो गया, so this is really high, meter per second. What should be the case with which a car must traverse a flat curvature? Okay, ये flat curvature क्या है? So this is turning out to be mu gr is meter per second. Okay, let's move on. Next question. Okay, तो देखिए ये बहुत ही इंटरेस्टिंग प्रॉब्लम आई है, ये सर्कुलर मोशन से है और इसका कॉम्बिनेशन है सर्कुलर मोशन एंड हाइड्रोस्टैटिक्स, ओके? So you know there is a hydrostatic pressure, it develops, and अगर आप एक U-ट्यूब लें, ओके, और उसको रिवॉल्व करें ओमेगा से, तो आप देखेंगे अंदर वाला मिनिस्कस थोड़ा डाउन हो जाता है और बाहर वाला मिनिस्कस अप हो जाता है, राइट? इस पर्टिकुलर केस में ये पूछा गया है, a U-ट्यूब contains a liquid with density rho. It is rotated about the dotted line. The difference in the level of the liquid column. देखिए difference in the level क्या show करता है? Hydrostatic pressure jump. That is rho g h. अब ये देखिए, अगर ये U ट्यूब है, राइट, तो इसमें ये हाइड्रोस्टैटिक जंप किसकी वजह से है? देखिए यहाँ पे जो मास है, यहाँ इतने रीजन में, ये तो एक्सिस ऑफ रोटेशन पे ही है, सो इट डजंट कंट्रीब्यूट एनीथिंग, राइट। और यहाँ वाला मास यहाँ तक है, ओके। तो देखिए यहाँ वाला मास ये कंट्रीब्यूट करेगा, राइट। और यहाँ वाले मास को ये भी नहीं कंट्रीब्यूट करेगा, क्योंकि इसमें सेंट्रीफ्यूगल फोर्स आउटवर्ड होगी, ओके। तो ये वॉल के खिलाफ हो जाएगी, इस एक्सिस पे कन्वर्ट नहीं होगी, ओके। तो केवल यही रीजन है जो कि सेंट्रीफ्यूगल फोर्स जनरेट करता है। अब देखिए बहुत ही इंटरेस्टिंग सवाल है, क्योंकि इसमें सेंट्रीफ्यूगल फोर्स वेरिएबल है। देखिए अगर हम कोई ये फ्लैट पोर्शन लें किसी x डिस्टेंस पे, एक्सिस से dx एलिमेंट, राइट, तो इसमें मास कितना हो जाएगा? सपोज इसका क्रॉस सेक्शन एरिया a है, a dx टाइम्स रो, रो v is dm, राइट। नाउ दिस dm, यहाँ पे जो dm है उस पे फोर्स कितनी लगती है? सेंट्रीफ्यूगल एक्सेलरेशन a होता है ओमेगा स्क्वायर x, राइट। तो फोर्स हो जाएगी df, स्मॉल फोर्स ऑन स्मॉल एलिमेंट, ओमेगा स्क्वायर x इंटू dm। dm कितना हो गया? रो a dx, राइट। अब ये फोर्स हमें निकालनी है, कोई लेंथ जीरो से f फोर्स और लेंथ 0 से L, राइट। तो ये जो फोर्स है यही आपका हाइड्रोस्टैटिक प्रेशर जंप क्रिएट कर रहा है। सो द प्रेशर जंप्स टाइम द एरिया, ये हो गया फोर्स, ये इक्वल हो जाएगा ओमेगा स्क्वायर बाय 2 एक्स स्क्वायर बाय 2, ओ सॉरी एक्स स्क्वायर रो ए, और लोअर लिमिट 0, अपर लिमिट L, ओके। तो इससे हमें क्या आएगा? इसमें अगर हम वैल्यू डालेंगे, रो गया, ए गया, ये L हो जाएगा, ओके। तो ये आ जाएगा 2GH is ओमेगा स्क्वायर L स्क्वायर, ओके। तो इससे हम क्या निकाल सकते हैं? जो H होगा वो क्या आएगा? ओमेगा स्क्वायर L स्क्वायर डिवाइडेड बाय 2G, divided by 2G. Okay, let me write at a better place. From this equation, H is equal to omega square L square by 2G. तो देखिए हमारा ऑप्शन क्या हो जाएगा? A. अब ये प्रॉब्लम वेरिएबल सेंट्रीफ्यूगल फोर्स की थी। अब देखिए बिटसैट में इस तरह का सवाल आए तो आप लोगों को ऐसा सवाल अगर डायरेक्टली पाथ टू सॉल्यूशन क्लिक हो जाए तो भी पहले 2 घंटे के बाद करना है, ओके। नेक्स्ट, ओके, सो द सेम आंसर, ओके। थैंक्स अ लॉट फॉर योर अटेंशन। देखिए आज मैं एक छोटा सा सेक्शन लाया हूँ, पर अभी मैं नेक्स्ट जो है रोटेशनल, ग्रेविटेशनल, प्रॉपर्टीज ऑफ मैटर, ये सब टॉपिक करूँगा। अब मैं बताऊँगा, ये टॉपिक बहुत ही इंटरेस्टिंग है, इसको आप बिल्कुल भी छोड़ के ना जाएं। रोटेशनल थोड़ा हार्ड है, लेकिन आप देखेंगे ओके इसमें भी उतने ही सवाल हैं जितने इसमें आए हुए हैं, तो ये टॉपिक छूटना नहीं चाहिए। उसके बाद ग्रेविटेशनल बहुत ही इजी, और इससे डेफिनेटली 2 सवाल आते हैं। ओके तो प्लीज स्टे ट्यून्ड, एंड आई एम गोइंग टू डू पॉसिबली ऑल 3 टुमारो। ओके योर व्यूअरशिप इज इम्पॉर्टेंट, सो आपको नोटिफिकेशन पहुंच जाए, इसलिए प्लीज सब्सक्राइब द चैनल। Thanks a lot for your attention. Have a great day. Bye. Okay, just wait. Okay. Okay, I didn't see this last comment. Anyway, thanks a lot for your attention.